guess with that, we can just directly start the demos. So remember, for the demos today, try not to make boring pitches. We want to see your application, and ideally someone else will be demoing it. It's fine if you don't, like, if you didn't have time to deploy. So in that case, you can do a boring pitch. Just try to make it not that boring. And also try to like really emphasize the tech stack, like what you used for this, like what frameworks, what worked, what didn't. I think that's like the most interesting thing here. All right, so anyone wants to volunteer to go first?
All at once, everybody.
Okay, yeah, I guess you guys already shipped.
Yeah, I think that's the point right now. It's all I mean, there's not a lot of AI in this one. Yeah. So who do we build this for? We built this for. Who did we build this for? No, I built this for me to prove my flat earther friend that rockets, no, that space is round. That is what I built this for. And yeah, me and my girlfriend built 2 rockets. So these are kind of kits that you can build, and they come with like the predefined like box and shell. But we mounted the motors today, and we got the parachute in there. What we learned is that like basically there's single deploy rockets and dual deploy rockets, and we're navigating basically how you design the rocket. So we're going at a single deploy rocket, and basically what we learned is that they have fuel in there, they burn up, and then at the end there's black powder at the top of it that has a delay, and then that blows up, and then that is what separates this and blows this out of here and blows this out of here, and then the parachute comes out of here, and then another parachute comes out of here. So we basically learned that and a lot of different things about like center of gravity and how to actually get this to go straight. Yeah, trying to think if there's anything else. Farsh, is there anything else we've learned? It's so fun. Yeah, we learned a lot. Yeah, we learned a lot about just like the certification process to get different motors. So if you want to get like to the motors that go to 40,000, 20,000 feet, then you have to get certified with NAR or Tripoli. And when you do that, you have to do a dual deploy rocket. So it has to have altimeter in here, has to have dual deployments. It can eject this part and the forward tube out. And then if you can do that and it safely lands and it's reusable, then you get your certificate. And then you can get bigger motors that can go farther. So yeah, we'll launch next week in Amesbury on Saturday. It's a free event. If you want to come, you can see the rocket launch. That's it.
Can you say like what's inside of this rocket? Like how exactly it flies and like what went into construction?
Yeah, so again, I just take it off here. So like there's like the shock cord, and then there's the parachute inside of that, and then if you take like this part out, there's the motor retainer down here. So it's kind of like all the actions down here where like there's a lot of like JB Weld and epoxy holding it together, so you can put the motor in there, and then you just get like a dry powder motor. So it's like the SD rocket motors, and they're just dry fuel. I don't know what they're made of, but then you just throw it in there, and then you use the ignition, and it goes up.
Oh, wow. And like how much fuel and like what's the laws?
There's so much to that. We did a lot of research on that. There's different arcs of the rockets. So some rockets have long delays, some go for a long time, they have different delay times. So like you have to figure out your rocket size and how far it goes, and make sure that the time delay for the black powder that explodes it to pop this out, you have to match that up. But the next stage for this rocket is gonna make it altimetered and dual deploy, and then it ejects it without an explosion. Or no, it does it. It does black powder. It uses the dual deploy thing to then trigger black powder here and here. It then also explodes it, pressurizes it, and then pops them out. So I thought I was surprised. Someone else told me they use spring-loaded to pop them out, but then like most people are saying they just use black powder explosive to like, it was like, oh, how do you remove this thing from here? I was like, oh, spring, something. Nope, explosives. And then you use black powder to like blow it out. Yeah. Any other questions though for anyone interested in rockets?
Do you plan to install camera just to see if the earth is flat or not?
Yeah, that is the goal. We have to get to 30K feet to get the good angle, but we'll like drill a hole in here, put a GoPro in, and we'll see. First, we got to get the rocket up, get the certificate, get the big motors, and then it's also an exercise in libertarianism too. Just to let you guys know, it's like, hey, I can launch rockets. Like, yeah.
And how much weight can it carry?
I think it depends on how you design it, really.
But like your particular one.
I don't even know what exactly it can carry because we're not putting much in here, just the parachute. So I think it could probably carry like 10 kilograms or so. Yeah, it can carry more than you think.
10 kilograms?
Yeah, that's what people were saying online.
So this thing can deliver 10 kilograms to like 5,000 feet?
That was no, it would go a lot lower. It would probably only go like 1,000 feet if you put that many kilograms in. But then 30,000 sounds very possible. 40,000 sounds very possible.
Yeah.
We just need the motors.
Okay.
Yeah.
Wow.
Yeah, actually space.
Wow. Alright, who wants to go next?
We need them doing this soon, right? Project from shares.
No, so you guys, yeah. We can either just connect to HDMI here. I think it's that.
Can you use that, like your laptop?
Sure.
It's on Zoom.
It's in Zoom.
Hello. Absolutely.
So I think they might take noise. Hi everyone. We were building Space Triage. It's more like AI guided ultrasound summarization. So Connie came up with the problem of, like astronauts don't have access to medical devices in space. So the most easiest and approachable solution is ultrasound machine, which is pretty small and can fit within the spaceship, I guess. The problem with ultrasound is that it is not very clear and it is very noisy, the images. Uh, so initially we thought of a plan where you can use the ultrasound image and then use a segmentation model to segment small parts of your organs and then have a reasoning model kind of, reason over it and summarize what the problem actually is, or is there any problem, first of all. So another problem is that astronaut might not have the full knowledge of the human anatomy. So whenever he starts scanning the body, he might be, kind of, mislocating the scanner on your body and like it might not be capturing the correct organ. So uh, we have here is a demo where you can enter the target organ that you want to diagnose and you just upload the image of that organ. Uh, yeah, so for example, like we are currently diagnosing liver and we have this image which we upload. So first thing what happens is we identify if this is a liver or not. If it is a liver, it goes on to like diagnose it and give a summary of what is happening. But in case it is so yeah, like here. So initially we were using SAM2 to segment the liver from that image, but it wasn't working as well as it works with MRI and other kind of images. So we removed that and like we directly are going with GPT-4o for now. But yeah, like if it doesn't, if we are targeting say heart, can you put heart over there? And you upload image of a liver. Hopefully it misidentifies it. Yeah, so it identifies that it is not a liver, and it asks like, do you want me to help you navigate to the heart for a better view? So you can ask it to guide you. Yes, and it's basically like the scanner is like you can move it across your body. So if it is a live video feed, it can help you navigate the body to reach the correct organ. Now heart and liver are pretty common, so it's fine. But yeah, like say small organs or small muscular parts of your body, and then it gives you steps to navigate from that part to heart. So it may give you like go up or something like that. and then you can upload, like it will have the new image basically in the next step, and then you can see the summary of. But yeah, currently, like you will have to upload the image of heart, which we don't have right now. So yeah, and it will give you the summary again. So yeah, that's what we built today. But yeah, like we would like to work on this because the data is not sufficient. Maybe training a small VLM for like the images of ultrasound would be helpful to get better insights. Yeah.
Do you guys benchmark how like GPT-4 performs on this type of data?
Sorry.
If you benchmark the performance of PLM, like does it actually do?
No, we did not benchmark anything yet. We were trying to play around with the segmentation models. So we found a couple of models which are fine-tuned on medical data, but most of that data was MRIs and other kind of X-rays and stuff like that. There's not much data sets which have properly annotated ultrasound images. So
Did you have an annotated data set? It's for you.
for this one,
Yeah.
like we randomly took these images from some random data set. So
Like,
no.
do you know like how to identify it yourself? Like, can you see a liver?
Can you see a liver?
Can you see a liver?
No, I cannot see anything. There's a heart image wherein the model identifies that it can see 4 chambers, but it's like very dark. So that's why it's like very hard for small models to do that.
I could have a good example.
Yeah.
Can I comment in? Is that okay? I don't know if anyone can hear me.
Yeah.
Yes, we can.
Hey, I'm Dr. Fischetti. I'm sorry I can't be there. I just got back from work. But I love this because this is a real life problem. Point of care ultrasound is currently the only diagnostic and therapeutic modality in space. Portable MRIs and X-rays are being developed, but ultrasound is the only one without radiation, which radiation, especially in space, is a big issue too. The one thing that's very difficult, having worked in the AI space specifically within ultrasound, is that ultrasound, unlike MR and CT imaging and X-ray imaging, I mean, there are like thousands, millions of more frames per clip compared to like CT images and MRI images. And so what makes it really hard to create the AI models is because there's, hundreds of frames even within a 6-second clip. And so that's why the annotation can be very difficult and why the models can take so long to train too, because the nuances are so different. And so right then you're showing just a still, what we call like a frame. Actual clip of it would be even more complex to annotate, but something that is, I love what you're starting to propose, because it's a real life problem that we'll have, especially as, we do longer duration missions. Currently, a lot of the astronauts, they rely on telehealth and they rely on just-in-time cue cards. And so you can imagine that as you go to Mars, that time delay and the lag is really unhelpful when you're trying to diagnose real time with, potentially limited satellite or signal. So this has been a great start. Good job.
Thanks.
Can I ask a question, like to Dr. Fischetti? I'm Connie, by the way. I'm just remote. So for this kind of project, the next thing would be to just think how to. We also found some videos, like this kind of from Stanford University from ultrasound. So for this kind of project, would the next steps would be to? Would you recommend like doing more like videos or actually just like still focusing on still images, but improving the training of the models?
I mean, of course, it's going to be easier to train models on still frames rather than video clips. Usually there are 3 to 6 second video clips. Like you said, it can be very hard to find open access data sets. And, I would say that if you are going to do that, you want the same image, right? So maybe just an apical 4 view of like 200 cardiac views. So you can imagine how difficult it is to get that. There are open access data sets, so finding the right ones, I think will be important. There might be some even within Boston through like the Mass Life Science Challenge. I know that they're creating a data set for something like that. But yes, to answer your question, I think the easiest first step would be to to do it really well with clips, or I'm sorry, still frames, and then to evolve into clips, because I think it'll be much more laborious to do the actual, video clips than the frames.
Understood. Thank you.
Yep.
So as you might have noticed, we have a guest, Dr. Fischetti. Thanks for the comments. And actually, I think we have a little bit of the time until we're waiting for research teams to wrap their projects. How many more teams we have who are ready to present tonight? So one hand per team, please. 1, 2, 3, 4. Okay. So maybe we can like take 5-10 minutes to ask Dr. Fischetti to present what you are working on, and like maybe share a little bit about the most interesting space problems that you encounter and like that excite you the most.
Yeah, and I'm so sorry I can't be there. I literally just got back from the ER. So I am an emergency medicine doctor. I work in the space medicine, the low resource setting division. We also kind of encompass wilderness medicine as well. It's a shared division between Mass General and Brigham. I am point of care ultrasound faculty, but within that space medicine division. And so specifically within my niche, what I look at is how do we come up with a way to basically enable the uses of the diagnostic equipment that's on the spaceship. So what happens right now is, these astronauts that go up, I mean, we're lucky if the flight surgeon is medically trained, whether it's a nurse, a doctor, a PA, but as commercialization continues to happen, you're going to have the layperson go up with the supplies and just, I mean, will it be enough to just give them the cue cards and like hope for telehealth? When you're talking about LEO, that will work, but when you're talking about a lunar base or going to Mars, those are real issues that could be really prohibitive for the layperson to navigate when deciding whether or not this is an emergency or not. And so part of my research has been, how do we condense all of this medical knowledge and make it digestible for the layperson as quickly as possible, knowing that AI is not yet there in the software and the hardware of the ultrasound machines. There are companies now that have like features like cardiac ejection fraction. Some of them help with like needle guidance, et cetera. But I'll give you a perfect example. There's in the medical kits and in the medicines that are up in the ISS on these space flights, you only have so many medications for so long. You have to understand that the pharmacokinetics of like the metabolism also changes for astronauts in space. And so here's a perfect example. Let's say you do have an issue in space. Let's say someone breaks something or someone's sick, and you don't want to use something strong like a narcotic. You can do procedural guided anesthesia, meaning like nerve blocks and things like that, which can be a very difficult skill to do with ultrasound. But AI guided nerve blocks can be far easier to do, especially for a novice. And so you can imagine that if you're now applying regional anesthesia and not systemic anesthesia, so think about like morphine, whole body morphine versus localized like lidocaine, what that could do to impact crew safety and who that astronaut is and the role they play on that mission. And so there are downstream significant effects to making sure that we keep everybody safe. Inevitably something's going to happen in space. Physiology changes in space. Just so you guys know, some of the biggest issues that happen, as fluid shifts in gravity or low gravity, environments, fluid shifts up. And so more commonly you deal with like bladder retention, kidney stones, DVTs, but usually DVTs on Earth are lower in the lower legs. In space, they can be in the upper extremities. Sometimes you'll have like localized skin infections, things like that. And then cerebral edema and kind of vision changes can happen as well. And so learning how to re-triage, how we decide what's an emergency, how does the physiology change and how can we help the bodies respond to that better are all important for making, space sustainable and for colonizing the moon and Mars. So that's just briefly a little bit about what I work on in the ultrasound sector, but my colleagues work on many other different things too. And so hopefully that helps a little bit.
Yeah, I'll just go seriously.
Yeah.
But
I have a question.
okay. You said just so you can see me. Hello. So I just had a question about like if you had to like go across these three factors, which one's the hardest problem? Is it the difference of their metabolic and thing? You said that it's different when they're up in space and their metabolic pathways change. Is that the biggest deal? Is it just knowledge and awareness because they're in a limited environment of just knowing basic things like cold skincare and what the problem is? Or is it this game of like we can only have so much space for so many materials and supplies. So it's more about this game of figuring out what equipment we can send up that has the most generalized approach to solve as many problems, like get the right match of equipment and tools. What is like
I
your
mean,
1, 2, 3 priority
I
across
know
those?
it's so hard. It's so hard to, and I honestly think a lot of it, I love that you guys are doing this think tank too. A lot of it is also like thinking outside the box. And I'll give you an example. Um, Two things that really come to mind are acupuncture, right? Because space and mass are a really big deal, right? In the actual spaceship. And so, you know, even like the size of a pill, like every single thing is weighed, measured, like it takes up an important part of what goes onto that vessel. So think about acupuncture needles. Is acupuncture a way to treat pain in space? Um, I made the joke, I feel like Ozempic should be funding some of these studies because reducing mass, reducing waste, reducing food consumption is also very important too. I actually don't think that's that bad of an idea. But things like that where you're trying to think of, okay, like what other ways can we look at this problem and solve the fact that like we only have limited supplies, right? And the further you go, the less likely it is that you're going to be able to like resupply. Um, and so I would say currently, I think it depends where you're talking about. If you're talking about a lunar base or Mars, certainly it's the mass and actual space ratio of like what can we take and how long does it last. For the ISS, like the resupply is a lot more feasible and realistic. Um, but again, part of it too will be how do you equip people? Because now we're going to have civilians going to space with less ideal physiologies. You used to have to be a perfect specimen. And how do you communicate to people that don't have basic, CPR, medical knowledge, whatever, knowing that they have only so much time to prepare? There's so many problems. It's so hard to tackle. But I would say if you're talking just from a physiology and like safety perspective, I think the biggest issue is how do we figure out what's an emergency and what's not? How do we do that quickly? And how do we decide, like, do we need to abort this mission? Do we need to like call for help? And then how do we decide which medications and things we need to use?
So you'd say identification is number one, then the game of what equipment and tools you bring up there too, and then just like the change in space environment's not that big of a deal. It's just like fundamental skin, whatever, like sicknesses, flus, colds, things like that.
Yeah,
Okay.
and even for something like ultrasound, for example, there are really good studies that show you can teach that to middle schoolers. You can teach it like, within a certain fundamental knowledge base, like to nurses. Like you don't have to be a board certified physician to be able to do that. Again, that gap will eventually hopefully be bridged by AI, but it's not there. And especially for ultrasound, it will take time because you need so much data to train these models on. And ultrasound is so nuanced in how you acquire the image, how the like every body habitus is different. So it can be really tricky to do that with.
Cool. The acupuncture comment was really interesting, by the way. Thank you.
They use it, and just so you know, they use it in the military. Like there's certain points within the ear, and they'll use it in like combat fields. But think about how small a needle is compared to like, I don't know, any other like sort of even the size of a pill. So thinking outside of the box is, I think, the way that we solve a lot of these issues too.
Thanks so much for sharing all this. I think it's very inspirational for us to see real scientists working right now on these problems. I think just because of the time constraints, we need to move forward. So I hope that teams who were struggling with deployment finally deployed. Is there any chance we can see the nebula? Very targeted, very targeted towards one team.
Two.
Testing right now. Give me a sec.
All right. Anyone who is ready to present now? Anyone who wants to volunteer next? Nice. Okay.
Okay, all right. Okay, so I'm sure that we're all aware that there are challenges in our society, like social, economic, and environmental challenges that we haven't yet solved. But a lot of people don't know that the information to solve these problems are out there. It's just hard to access. And these data statistics are often very complex and hard to navigate. And currently there are no AI-powered analytical chatbots that can process this information. So what we did was we created an AI chatbot called Earth Agent, and essentially what it does is it takes existing satellite information from Google Earth Engine, and then it'll analyze it and then process the satellite information via AI and then spit out easily accessible knowledge. So you might be wondering what Google Earth Engine is. It's basically a satellite data set. You can see like climate, temperature, agriculture, and population dynamics on it. So yeah, basically what we created was an AI chatbot that will bridge the gap of this informational issue, and it'll create inaccessible and complex information into simple and understandable.
Right. Does anybody want to come up and try it out?
We're just still estimating to
Yeah.
get this for map creation.
Yeah, so like essentially what it does is like what like statistics you want to see visualized on this map. I don't know, like population, topography, I don't know.
Yeah, how about an elevation map?
Yeah, we can do that.
To go and demo.
Oh, yeah.
Yeah.
I need more volunteers.
Yes. I don't know. Elevation map, different states, average to the square mile. Is that, I've never used this before. Does that seem fair? All right. Cool.
Whoa. I think my API key might be gone. Yeah, that's my API key. It just happened to run out. And I'm not gonna really. I mean, I guess I could.
It's recording.
Oh, yeah, that's a good point. I mean, I can get rid of it later, right?
Yeah, you can revoke the API key.
For like 10 minutes. It's a GP. Wait, no, I'd have to plug in my credit card information. I'll share yours. Does it inject though?
No.
Oh, it is. I'd like elevation.
Maybe my battery's low.
Plug this into, or?
Power.
Under right there, the sharing icon just went live. Okay, wait, mine works now. It's just the internet that's bad. Yeah. Alright. So I guess I can do this again, but that is Mike's prompt above. And then all you do is just generate the code for the visualization. And yeah, so it gives us our code, and then we can directly inject it here, and we can just run it. Hopefully. Sweet. Yeah.
What's the prompt?
So I think here it did have some trouble, but in the other, like we have other examples. So like it's still running.
Choose the inspector to see the layers.
Right.
Wi-Fi is really slow.
Yeah.
Still running.
Maybe I picked bad prompts. Yeah, maybe go with that. Free can one. Sorry. I mean, like these are some other visualizations that is able to create. So like population density in Texas, give like a pretty high definition graph or diagram, and you've got like elevation of Mongolia, which it just automatically gave, and so, like it can even do like flight paths, um, and just like anything up to your imagination. Um, okay, Chuck.
Could you do bison migration paths in the Midwest?
We can give it a go.
I mean, so is this could come since it's the one with it's Google stars. And then you can sort of
They give, yeah, it might have trouble with the data set because it does pull up old ones. Yeah, the data set just, I guess, is too top secret. Any questions or further requests? Yeah.
I have a question about Google Earth. So like the data, is it coming from Google Earth or your prompt like finds the data sources?
Yeah, so the prompt is able to
find the data source inside Google's databases.
So Google Earth gives you like access to the data.
well, yeah.
But Google Earth or Google database?
It's Google's databases. Wait, actually,
It's a Google Earth data catalog. We have share data.
Because getting data from like the internet and overlaying it would be super hard. But okay, I get it.
Yeah. So the data and the computers also they're together. They're connected together. So that's why that's the big scale. But the data is it's a lot of data there, but it's still limited. And the prompt will generate the data location over there. Again, URL.
one of the key issues is that OpenAI doesn't really know what are good databases names. And the failure with the Python is that it doesn't know which database to look for inside the catalog. We might improve it with some search function later.
That's all.
Hey everyone, we are Astra, and our project was about creating a tool that minimizes the energy used in agent-to-agent communication for solving complex tasks. And so in the demo that you see today, we provide a use case scenario of AI agents exploring a space, like exploring a space such as, Mars, and communicating to achieve a goal of identifying water, and you'll see how that performs.
Yeah. Yeah, I can talk a little bit about the back end. So what we did was we made two rovers. They're like filled with a little fake information right now, but they would be like in theory they would be actual information that the rovers on Mars would collect, and it would be in two sort of sets. So rover one hypothetically has all the solutions and has an empty dictionary filled with like observations that rover one would, or rover two, sorry, would then put into rover one and report back. And then rover two, if they come across any problems, they say, hey, rover one, I have a problem. And then rover two or rover one gives the key problem, returns it back to rover one or rover two. It's a little confusing between rover one and rover two, but basically rover one has all the solutions so that rover two doesn't have to carry that much information with it. And it can also just constantly update with a human in contact with rover one. Yeah.
So for these rovers to interact, we implemented two agents using GPT API, and they're pretty much having a conversation with each other. So if rover two comes across a problem, it'll ask rover one like the potential solution for that problem. So that was our agentic interaction. And in the demo we have like a parent, and then we have a bunch of children rovers. So the goal is to uh, go on the surface of Mars and try and find water. And the other thing that we implemented was tokens, because we wanted to see how little tokens can we use to convey a decent amount of information. And that's like based on like bandwidth, because there might not be as much bandwidth. So you want to reduce the token size. So less tokens means less information, but how efficient can that information be? So that's another thing that we tested as well.
Okay, demo time. Okay, so to show this, you need to see two teams, right? So one team competing under different conditions than the other team. And the key thing what we did is we enabled new way of agent-to-agent communication. Why? Because yeah, we're communicating under very low energy, very low bandwidth, and difficulty trying to reach each other. So we came up with that the key problem that we have and rovers in space is how much tokens they can be exchanging. So we actually came up with a few ways of compressing the token output from one agent to the other. So we used contextual expression that Sophie talked about. We're using some semantic compression by using the neural network itself. So in this case, OpenAI is the network that is embedding the compression, yeah, on the output that it's generating. And the last thing, we're doing some fingerprinting, basically some hashing on the tokens that are sent out to the other model. And because the models are exactly the same, we're leveraging the same representation of concepts that they know about. So now, how does it look like? So we'll give blue team a compression here in this case.
we'll turn up the tokens for both, just to speed it up a little bit. Set the maximum token limits, just let's say to 4,000. Let's launch this mission. Now, what is happening? So we have, in this case, 3 red agents, OpenAI in this case, 3 blue agents, and they're looking for the water. That's the light blue dots. Well, we see what's happening down here, and we see that the agents are communicating about what you're going to do. So one moves north, west, and east. And then blue is using a very different way of communicating. So it's basically sending S72-15.45. Now, it comes down to pretty much a similar way of coordinating, but why it helps is that you see the compression. It's saving about 90%, so an order of magnitude in its tokens that it's using in the coordination. And that's what we're going for, because coordinating is pretty energy intensive. And you see the tokens that they're racking up. So red team is already at 1,100 tokens in this game. Blue is still below 100, now passing 100. They're a little bit lucky that they already found 2 sources of the water. Yeah, so what this is just showcasing as a demo is that agents, if you let them communicate, let's say in small groups, they rack up tokens very quickly. On the first one, we made a mistake. I made a mistake, and it reached 80,000 tokens in not even 2 minutes. So, and there was no like kill switch or stop button. So this is important. If you have, let's say, groups or swarms of agents cooperating, you want some way of really efficient communication between those. So yeah, we're managing here more than an order of magnitude. Blue team is ahead. I think, yeah, this game will go on for a little bit longer until blue finds all or they run tokens. Yeah, but that's it. So it showcases ASPRA, which stands for, of course, agent to agent, meaningful token minimization exchange in extreme conditions, under extreme conditions like space. Does it make sense? Yeah.
Okay, about future plans. As you could check, this is a new even research topic. I'm serious. Really, like, if we are serious about like using LLMs in space, this is a serious matter also because as you probably may know, the energy consumption of even the inference of these models, it can be really costly. So yeah, the next level, I mean, the next features that these simulations should have is like really realistic setup, like from the energy point of view. This is one of the, let's say, most limiting factors in space. So you have a certain amount of energy, you have a certain roles. You have, for example, 3 roles. So one role is just the explorer, the other role will be the driller, and the other role will be the transporting machine. So you have these 3 roles. Both, like all these 3 roles have like limited energy for all the actions. So you can, let's say, move or you can communicate, and the communication also costs energy. So in that environment, do a realistic, let's say, simulation of this compression protocol, which is very, I mean, if you think about it, it's not like, doing WinZip. We are using the structure of the model itself. So with no prior knowledge, one model can communicate with each other and understand what they are talking about with less token. I mean, this is very interesting. Thank you.
How did you choose the compression for the token?
He started.
So we first did some semantic compression, and then the idea was, well, we don't need a separate model to do semantic compression like a semantic model. We can actually use the model itself to do the compression. Then we did some sort of contextual fingerprinting. So based on different states, we pre-programmed, like if you're sending this message, it has this meaning. And so you can also, you already worked out like that they can create their own blueprints and encode it into one token, basically. So they can share this new way of very efficiently representing a new situation. Hashing is going on. And if you put that all together, you get very cryptical messages that we can no longer read, but you can also decode it in the same way, of course. So that's also that's happening under this. So we see they're just sending like messages like this. Yeah. Yeah. So semantic fingerprinting. I think that's a nice way of putting it.
Okay. Yeah, cool. Any other questions?
It's how much prompting is involved. Like, do these have like massive system prompts beforehand to like lay out the compression stuff that you guys are doing, or is it like relatively terse?
No, very, very limited. Actually, we started by just putting in the objective in the top, but then we had to redo and redo that. There's just a simple objective: find the water, and then the only thing that they can do is communicate with each other sequentially. So they each get a turn, and then they communicate to their team members, and then they get the next team member gets a turn. And there's no other system prompts except the token limit that they have to adhere to.
Okay.
Yeah, and that's it. So it's very limited. Yeah.
What a lovely demo, by the way. It's so cool. I love it. Super cool visual. But yeah, which layer was the most brought the most performance efficiency? Was it the hashing? Was it the one token blueprint type of thing to speak their own language, or was it the one rover out to many other rovers?
I don't know. I think we implemented
all at once.
Yeah, multiple things at once.
Okay, and then when they like communicate with each other, it's like, does the decrypting and encrypting, is that like take extra energy when they're decrypting and running that, or is that super efficient?
I think that for decrypting or encrypting, that definitely take extra energy because you need to do a lot of computation, which consumes a lot of energy on that. But compared to while you are traveling, that's still gonna be minimized. Not like you are going to train a AI model using a lot of GPU spaces, but that one can be almost minimized.
No, but I think it's also a matter of research. I'm not sure 100% what's it. I mean, it's true for, let's say, encryption in general as a concept, but I'm not sure if, doing the thing that we are doing, it will, how it will work.
Yeah, what's one token versus encryption, decryption for energy?
No, really, it's a whole research topic. No, it's serious.
Very cool demo. I love it. You guys thought about it very differently than I would have. I would have thought of it as just a byte stream, and traditional compression would have been like my go-to. I'm curious, did you guys compare that, or? Yeah.
It's a very good point also. Yeah, to have that baseline. Yeah.
And also in our case, I think we are, instead of using like human understandable language, we are also ask AI to build their own language, try to do the encryption and the decryption. Basically, it can take like some into the next level of encryption knowledge, which we were never used to do before.
Right. You're just kind of getting into information theory, and like I'm curious how much you can encode versus like an ideal compression is very close to entropy. So, yeah.
Yes. We talked about it. We talked about bioinformatics and the tree. But then we thought, well, actually we have a full representation of all the knowledge that has been going into this model. And let's try to leverage the neural network, because the other rover or the other space part has the same model and is carrying that same model. So why would we?
Yeah, maybe that does get you.
Change. Yeah.
beyond the limits. Maybe the limit for traditional compression. It doesn't presuppose having this large corpus of knowledge. I don't know. It's very interesting. Yeah. Yeah. Cool
No, I
project.
mean, this comparison should be in the paper as well.
Yeah. Yeah.
And just do they have a strategy to find the water? Because I feel they haven't found the 3 water already.
No, blue. Yeah, they're still
looking. Do they have a strategy or?
Well, I think what happened here is that, yeah.
Okay, that was a bit concerned. But also, do they have a strategy or?
I don't know if it's code like if a particular strategy is coded into how they move, but we did have a conversation about what kind of algorithms would be used for exploration, and that's this is just one task. Exploration, it could be applied to many different features of large language model teaming, and so I think the algorithm would change, but I think these efforts were for what happens when we just give it a prompt and tell it to go.
We're really literally seeing OpenAI 4.0
Trying
to just communicate through a text prompt, so many tokens max, and then the others are responding with a new move, and then it's like the basics.
Yeah, cool.
I mean, this is the gentle way, like to find an algorithm. The brute force way would be, hey, this is your energy that you have for accomplish this task. If you get run out of your energy, you are fucked up, and you need to figure it out what's best, and try the models in that situation. How do they perform? It would be interesting to see.
Maybe you guys mentioned this, but is there a particular problem with game theory that you got inspired with? Why exactly this setting? Is there something that's already studied, the same type of game?
No, we didn't go into game theory or really delineate it nicely, like this is a fully observable game, with sequential moves and do that whole state space, but we basically started from the situation, so how can we get agents to cooperate with the least possible amount of tokens? That's what we came to, that's our essence actually, that's the core. And all of this is just the space case we've been now using to show what happens. But I think, so the heart of the exploration today was limiting the amount of token usage and agent cooperation to the bare minimum and see what happens. And Blue still won the game, even though they had so I think
should definitely make a blog post or at least workshop paper.
Yes.
We should near deadline is in 1 month.
So Sundai papers.
No, really, you guys. There's so much interesting questions.
Yeah. But it's this exploding amount of tokens, right? When you have a lot of agents that start to communicate, it's this exponential curve that we're getting on. And if we're not trying to get the other exponential down, it's going to become too large for agents to effectively communicate together. So I think this is.
So next week is going to be growth. So workshop with New Reefs is only two pages of you can do it in a day. That's something that 100%.
What happened to the frolic?
You vibe code LaTeX. That's how you do it.
Okay, so thank you.
Thank you.
Yes.
All right. I hope you all enjoyed that very serious, useful research topic. We're the pretty picture team. Um, we, we did nothing of scientific value, but hopefully it's cool to look at. That demo is going to be hard to beat. Oops. Wait. So yeah, we worked on a product. Run it updated. We worked on a product that you can upload an image of a nebula or any other astronomical object, and it will create a 3D model of that object and allow you to zoom in past all the stars into the nebula. So here we have it running, uploading one of the photos. Not seen this one. I've seen one demo photo so far. It was pretty good. So we'll see how this one goes. Oh yeah, we got music. So yeah, that's what we did. Way harder than you think it would be to do something like that. Labeling all the stars in the images is basically impossible to do automatically. Who would have thought that like 4, somewhat blurry pixels, no program out there to go and figure out, what specific star it is. So yeah, we ended up having to, the positions of these stars are not accurate to real life in terms of their depth. They are just randomized, but these are real stars in their locations where they would be normally. Under the hood, we're taking the image that you bring in, and then we're running a machine learning model that goes and removes all of the stars from the image. And then we're mapping distances onto all of those stars to go and create basically a 3D model of those stars in front of the nebula. And then we're adding them back on top of it and then sending a camera in and out to zoom past all of those.
Yeah, also for the starless image, we analyze the depth of that image with like AI, and it's essentially what you see in the middle, like the heart-shaped nebula. It's also 3D. You would be able to zoom it closer, and actually, it's like has some shape to it. What else do we have?
I know that was most of it. Not think we have anything else. We have a gallery of a bunch of different ones that we have done that we processed. These are all amateur astrophotography photos taken from a site called Astrobin. So shout out to publicly source these. And then running our program through it. It can handle any image. It's local host right now, but we should have it deployed later. We need to get a better backend because it's running a machine learning model. So there's no easy deployment options for that. Hopefully have that deployed. So you guys can play around with it later. Upload whatever photos you want there as well.
How do you guys, like you said, that the nebulas themselves are also 3D?
Yeah.
Is it mono depth estimation or?
Yeah, it's like a simple. Actually, it's right here. I think there's model depth analysis like we do on Hugging Face.
Oh, it's definitely.
Actually, like I played with it a little bit. Like for some of them, I actually changed the depth manually to make it better. But you can just use it as a start.
How much expensive is like computationally speaking? Like how much does it take to generate this?
It's not too bad. It's more memory intensive for like running on like low-end servers. I think the model's somewhere between like around 2 gigabytes. But time-wise, it takes under a minute to go and generate the whole thing. It's all we're actually doing. All that we're generating behind the scenes is the starless image, and then the star, or what was the third one? The mask of the stars and the starless image. And then we're just sending those all to the front end, and this is actually being rendered live in your browser. This isn't like a pre-made video or anything like that. Theoretically, we can have like a slider. You can slide it in and out manually yourself as well, and it can render it in real time.
Yeah, super cool for a immersive experience with the Vision Pros or something.
Yeah, I mean, it was supposed to be like when you zoom in and zoom in, you would continue zooming in. We just didn't finish it. In the end, you will see a little alien.
Or like, yeah, we were gonna show like the flat Earth or something as you zoom in close enough.
What's the masking model? It is a specific one made for astrophotography to mask out stars and remove them from images.
Yeah.
It's
starting at plus plus.
Yeah.
It's a GAN and it's only 200 megs. So like you run it on your CPU, which is also why we were hesitant to deploy it because the free version of deploying this is like a 0.1 CPU core. So you saw it took maybe like 30 seconds to a minute to process the image. It would have taken like 10 times as much.
And the 3D library you use?
But if you're here, we can set up with the team members. And then we should see some.
Okay. Yeah, there you go. I see I started plus plus. Another one. Is it possible to make this look like a wallpaper? Probably, yeah. Yeah, it could just be a live view wallpaper. Yeah, we talked about having the option for, but yeah, you could theoretically just export this as a video, and then have that, and then set that as wallpaper. Yeah.
I mean, the plan is like actually like to take a picture with a window in it, like preferably, and then it would zoom in and fly out of the window in the universe, and so that would be wallpaper like idea for you, like to have this kind of nice photo that will go into space.
Like bedroom window, like, you know, like a nice like mid-journey generated bedroom, and it's got a fancy window, but it just looks like the night sky, but then it zooms out of the window and into the night sky, and then you stumble upon a nebula.
Thank you.
Sure. Okay. So sorry we don't have cool space stuff, but we're gonna talk about GPUs. Sort of to set the stage, the justification, like models, especially like large language models, have gotten like huge, and now we can't even load them on our GPUs because we don't have enough VRAM, right? Especially for fine tuning stuff like that. So there's a technique called gradient checkpointing, where what you basically do is for some layers, instead of, you know, how like when you do a whole forward pass, you have to say, well, AutoGrad saves all the intermediate gradients and you do that to compute the backward pass. But instead of doing that, in between in between two places of computation, we just discard everything, every intermediate gradient. And when we do the backward pass, we only save the input at that point, the intermediate input. And once we get to the point where we need the gradient there, we just do the forward pass again. How does that make sense? So we have like some checkpoints, bam, 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 bam. There's the whole model. Once we do the forward, we go back, we do the forward again to this point, and then do the forward this little segment of the model to compute the gradients. That way we can sort of chunk the computation in a way that we have enough memory to use it. So our experiment really was like, how much should we checkpoint in like a model? So we use Qwen 1.5 billion, right?
Yep.
And the trade-off here, of course, because we do extra forward passes, then it'll be slower. There will be less tokens per second, right? But surprisingly enough, of course, doing full checkpointing in every single layer, it's the slowest. But the trade-off is huge, as you can see in this graph.
We have a large increase from like recomputing everything to like recomputing every other block.
Right. So to explain this graph, the y-axis is so in the red line is the maximum gigabytes of VRAM that we're using, right? So ideally, we don't want to get more than 100 something gigabytes because then we get out of memory. And for the yellow line is how many thousand of tokens per second in average the model takes, right? So we see, and the x-axis is sort of the checkpoint frequency. So one being we checkpoint every layer, two being we checkpoint every 2 layers, so on and so forth. So we can see like checkpointing every layer reduces the VRAM by a lot, like what is it, like by a factor of 3, while we only have like the slowness that it produces if we don't if we do checkpoint. It's probably worth it. It's about 3,000, right? Mm-hmm. Right. Yeah, so
down to the tokens.
right. Yeah, you want to share the other graphs?
Yeah. So something that might be a little more visually appealing is looking at sort of the memory footprint of these processes
in one single run.
Yep. So we did some memory profiling, and you can see like just the little intricacies here of you know, if you're like recomputing everything, we get these
So this is checkpointing every single layer. You can see how the memory footprint is pretty low
yeah,
overall. And then if you compare it,
there's like 12 layers, right? So
right.
So there's like
12 little spikes. Yeah, well, every like intermediate forward pass.
What are the big spikes over there?
That's when we calculate the loss, right?
Yeah, this one there's technical loss.
Like the whole loss of the model.
Oh, so it's like the final layer of the model.
Yeah, exactly. So that's and it's just 20. Yeah. So that big spike like stays constant over all the runs, but if you can see like on like this is the big spike that we see here, right? So here our maximum was like 95 gigabytes. Like this is if we do the gradient checkpointing every 2 layers, right?
Yeah.
Yeah, every other block.
Every other block, yeah.
Uh-huh. So this spike right here is the same as this spike, right? So it's very tangible, the difference.
Yeah, but you can see like the memory footprint
right
here gets quite large.
Yeah, and if we don't do gradient checkpointing, we can't even run the model or for fine tuning because we just don't have enough memory. And this is with a huge like what was it, like 120 gigabytes of VRAM, which is much more
Yeah,
than
so
anyone.
it's not just quantization, folks.
Yeah.
Okay, gotta mess with the techniques.
Yeah.
What are you using for your model trainer? Like, did you roll your own or?
We use some like harness code that was given to us to like fine tune.
Yes, it's just
So it essentially like PyTorch.
Boilerplate fine tuning code.
My comment would be, so you're training on batch size like 1 or 2 on 1.5 million parameter model.
Right.
Okay. It should not be taking 95 gigabytes ever for memory usage at some point. It's usually that the math works out to it's about 12x the number of parameters is the full fine tuning memory usage. So yeah, it's like you can fine tune it on like a 3090, like 24 gigabytes of VRAM at batch size 1. Would be my guess. So my thought is that I think there's a bug somewhere in your training code. Because yeah, the utilization numbers are way too high.
Well, it is around 40 gigabytes if we do full gradient checkpointing, which is what most people do now.
That's without any gradient checkpointing.
Without any gradient
It's without any, yeah, when you introduce gradient checkpointing back in, I think you can reduce it by about a factor of 2. I don't know if you guys looked into it either as well. Sorry.
No, you're good.
But, for gradient checkpointing, usually what you do is it's selective gradient checkpointing, not on a per layer basis, but on a per operation basis.
Right.
So like for instance, like dense matrix multiplications consume the most amount of compute, but then stuff like layer norms is very easy to compute.
Right.
And so you will selectively recompute layer norms and other easy operations. But the dense linear operations, you won't, you'll keep those in memory. And so that's what people tend to do. And you get like 50-ish% less memory usage than you would from your gradients.
There's going to be more research events.
It's going to join today.
Oh, yeah.
That's a good question. So if you train on 60,000 say transformers with like PRL as a trainer, you'll go up to 1.5 million more.
I guess, yeah, what sequence like you're training on?
Yeah, so
That's something I guess, yeah, the numbers I have, I think for sequence. Okay.
Yeah.
So then it's 4x more, so that would be about it. Actually,
Yeah.
yeah, well, so yeah, what sequence? Yeah, that is true. Yeah,
Oh, Nisha, I guess like that's what you researched one of the previous Sundays, right? That like you can chunk the final logics layer before you connect it to the maps logics to drop the point.
Time, I can talk about that. Yeah.
Yeah, that's the other.
I think this is already using some tricks too.
Mhm.
Okay, we still see this part.
We still see the final logic spike to the giant. Definitely need to chunk them further.
But I also did the profiling of packet-based transformers. That one done.
What do you mean? It's
Basically the OM. Like if you you can put one batch with 16K, it's fine. I think the limit is about 20K plus, it's eventually flies. Here is still some memory that you don't put on. It's the demo dot It's a super labor question. Just want to check what is a checkpoint is. What is a checkpoint exactly?
Yeah, so the naming is a little tricky. It's not like you're saving the model. Like checkpointing means for a given like subsection of like the computation graph, we save the input, like the start of it, but not the intermediate gradients, right? So when we do the backward, we have that saved input to do the forward, right?
Yeah.
So we are team chunkers. So we were trying to do different kinds of chunking and actually address those big loss spikes when that you saw on the previous plots. I mean, I guess the motivation already been given. It's we want to fine tune models on reasoning traces. So you have the CR1, it generates tens of thousands of tokens. And if you want to teach smaller models to also be good at it, you have to fine tune on this data. So that's, I think, part of the reasons why these techniques are still not very well explored, because people never needed to find such long context before. So that's why the default settings, default libraries, they don't do so well. I think soon enough they'll build better, but now there is some interesting questions. Okay, so what we tried is different kind of chunking. So even in the past, we already found through some GPU profiling that if you chunk your completions, so let's say instead of training on 16K, you still train on 16K, but you take 2000, compute the loss in 2000, you save it, you go on to the next 2000, compute the loss added to the previous one, and sort of keep iterating this way. So this already gives a pretty good savings. So let me first go through them. So again, we're using the similar profiler. So this is just the baseline. So it shoots up to 60 gig of memory. So the speed is about 3 seconds per iteration. So after we added the chunking I just described, so we can get it down to 43. You can ignore the result of 43. So that's pretty good saving. And the time is exactly the same. So next, so something interesting that we noticed. So we actually tried to build like a way to understand the GPU memory better, and we tried to use the profiler, but get like into really the details. So what helped is just literally printing torch food allocated memory. Put the script paper wherever you like, how much memory is there. And so this showed something interesting. So let's say here we print this, like this before, then after computing the logits and after computing the loss. Okay, so this looks good. It's much better than the vanilla implementation. But as you can see, so as they go through the chunks, the memory increases quite a lot. And that seemed a little bit weird. Like, why should the memory increase as it crosses the chunk? Like, in the ideal world, we should compute the gradient, and we can have it stored by some lot. So it seems like unnatural that it increases. And so that led to a next idea. So what if we do something similar to what gradient accumulation does? So gradient accumulation goes over batches, and it says, I'm going to compute a gradient on batch number 1. Then I'm not going to update my parameters.
I'm just going to compute the gradient of edge number 2. And after that, I can do this many times as I want, and then I will update my parameters. So this allows you to have larger batch sizes while still, being limited in memory. So why don't we do the same for the sequences? So as I go over my chunks, so previously I was summing up the losses. And somehow, for some reason, the memory was increasing. So we said, let's just do a backward after every chunk. So we thought this might help. And indeed it did. So this is after we did this, what we call accumulation chunking. So you can see we do not have any loss spikes. Like the memory doesn't spike when computing is lost at all. It's basically just gone. So we have a very clean so memory allocation here. So we are down to 23 gigabytes, which is pretty good. I would say, so one drawback I should notice, I think maybe with a bit more skill and implementation, this can be fixed, but now it takes long. So it was before 3 seconds. Now it's up to 18 seconds. I think there is it's just not done very optimally. It's a hackathon, so I have to rush a bit. But I think it's pretty cool. Like even with this speed up, like it's still valuable, even if that's unavoidable. Sorry, not speed up. That's time, because sometimes memory is really what we are bounded by. Like right now, I think you could maybe train on like 100K patients for just so yeah, so these are the main findings. So I also did a quick correction check. So this is just to make sure the gradients are identical. So running 10 iterations over the same data set. So we checked the cation similarity of like arbitrary transformer layers 15 MOP gated approach, just a random one in the middle. And so we double checked that the gradient are the same, just to make sure it's gradient snap. So we have vanilla, we have chunky, and we have NP chunk is what is accumulation chunk last years. So you can see that the gradients are all the same, numerical differences. So again, this is the time distance 0, it's the same, 1, it's a terminal. So yeah, so any questions so far? We have one last thing also.
So it's accumulation chunking, you're just updating the weights as you go along the way in chunks. That
you don't update the weights. You compute the gradients and then you just keep it. You don't touch your weights. Then you move on to the next chunk, you compute the gradient again, you add it to the previous one. And you keep moving along this. Okay. So this basically avoids this sort of weird grooves in the GPU memory as we go through the chunks. Maybe there are other ways to get rid of it, but that's kind of the one thing we tried. All right. So and then Felipe, you want to talk over the other thing? There.
Yes, I can talk about. Can you hear me?
Yeah.
Okay, so the final idea was an idea inspired by a function that we found on Unsloth package. So instead of like chunking sequences of text, what they do is that they chunk the vocabulary. So the idea behind like why this should work is that, like for example, we are working with Quen, and the vocabulary is like massive. It has more than 150,000 tokens. So like at the last layer, we would expect to have like a very big tensor, like with one of the dimensions being like the size of the vocabulary. So we want to avoid the computation of this big tensor so we can save a lot of memory. So what we do here is like we have this 150,000 tokens and we chunk them in like groups of 10,000. And we perform computations in this group separately, and then we aggregate everything together. And our results show that, so basically, we are comparing against the second idea, which is chunking with sequences. So this plot, as you can see, is the one chunking with sequences. And we use around 44 gigabytes. But if you go down a bit, we can see the other idea that reduces to less than 20 gigabytes. And then at the end, we have a table showing the losses are close to each other, and then both are going down. Yeah.
Yeah,
So
I think in this case of something changed a bit, but it's much faster. Did you compute the time for iteration?
Oh, I have yeah. I don't think but I think that the time was very close. Like both, they didn't differ a lot. Yeah.
Okay, so I think now if you put it together, maybe you don't need GPUs anymore. By the way, fun thing, a request to maybe the Sundai Club is, you know, we were really in rush writing this, so as you can see, the blog post consists of print screens. Like even for something like that, it was just quicker to just grab a print screen and shove it in here, you know, like trying to get a markdown table. So maybe that's an idea for an ad.
To what, parse the code from there? Or?
Well, now take this because it looks kind of unprofessional and maybe turn it into like a markdown table or something. Like, I mean, pictures are pictures, they're fine, I suppose. But like this is also a print screen of a text.
Yeah.
I mean, I think the probably like vision language models can get the numbers out and then like put it in markdown.
You can also probably make a button, so just like you press it and prepares a draft of a post about this insights on the
like
video.
make it look normal, like
yeah,
kind of like
to like make it look professional.
Yeah, that'd be pretty cool. Okay.
Do you guys think it's like, because it's kind of surprising that if you can get such a memory optimization increase, like it basically feels like it should be a standard part of like Transformers library.
Well, I think, well, I mean, Transformers has many issues.
Yeah.
But I think the reason it's so far like not so suboptimal is just because fine tuning on the super long, like even before we had RAP, but you don't fine tune on long completions. You have long context, and so in that case, these problems do not come up. Like you would not have the memory spike due to loss computation. So I think it's just people never had this problem.
So like, it doesn't make much sense to make a PR to Transformers.
No, I think for now it does. Like, I mean, but this code does not, it's a pure PyTorch, right? So if you wanted to work with transformers, we would need to like actually put it in the transformers to make the PR.
But when is it on Transformers or where did you get
No, the code is just pure PyTorch implementations that it did before actually.
Oh, so it's just like
plan architecture coded in PyTorch. With like, we were sort of just learning steps. That's I think the starter code. But I tested with transformers, so you can also do GPU memory profiling with transformers. So I could sort of use the same memory. Like the basic version, what I call vanilla, is
to also know that like there are like image on slot sort of specializing in that long context fine tuning regime where they have like that's where you guys said you found the other optimizations for. So I think them and then also Torch Tune also. And the Transformers library, like you don't use to train models if you're serious at all. It's on slot, for instance, like they do a lot of like key patching basically of the Transformers library and the models in there. Just because like there's so many models to support in each one, you have to go and like manage it. That's not a reason to go and update that entirely. So they just sort of like branch off of it instead. With trainers off of it.
I mean, this could be something fun to like tag on slots guys in the Twitter post and see if they like have they already done it or maybe they want to do something like that. Probably better.
wait, what's Unsloth's model? Do they have like a GitHub can contribute to or?
Yeah, Unsloth is like essentially like a GitHub where started with like two brothers also doing this type of hackathon style thing. Pretty much still them. So they essentially go through the code of like open repos or like implementations of LLMs and find bugs and issues. They also like they can write their own Trident kernels, and that's something also we can explore at some point. So I mean, a lot of things they've done was like, very good for LoRa fine tuning because there you multiply 12 matrices, and the default behavior of like autograd is like it doesn't do it well. You know, it doesn't sort of transpose things well. So that's one thing they did, but they also did a bunch of other stuff.
Right, that's all. right. I think that's it for today. I feel that in wearing this costume, I really have to play music in the background. So be playing something while speaking. There's not much, so thank you all for hacking on space today. It was super fun. I really had fun, like hovering around you guys. So finally, next week is going to be the long-awaited Rose Week. So that's kind of like the entire Sunday vibe. That we are not just like building hackathons and they disappear into the void. The entire vibe is that we are publishing them somewhere and we like make it something useful. So I think a bunch of teams from today should really come to the next Growth Hack and either like create a workshop paper or publish their Chrome extension or get some GitHub starts and like really just so it should not die in the shop. So please come next week. I guess for that, Gabby, do you have any announcements?
Thanks to Mike. So we have the link tree. I posted it in the cross posting. We have Twitter, Reddit. We're trying to build a community in several places, also Spotify. So please help us following, and also we are gonna start tagging you. So yeah, that's coming, but it's a community effort. So yeah, I think like if you check the link tree, like follow the community. Thank you.
All right. Alright, and finally, remember we are a community. We have a community call on Tuesdays at 8:30 where we discuss feedback and plan the next talks. And now give us feedback. And before you guys leave, please help us clean up. Take over the out, put the chairs back in, come back to your workplace, please clean up.